Okay, we are into chapter 9 here. We're talking about acids and bases. Thank you. So last time we got into this chapter and really a couple definitions of acids and bases that we talked about. First off, really an acid is kind of anything that can produce H plus or H3O plus, really free floating there on the product side of the arrow. And remember that in acid-base chemistry, H plus and H3O plus are essentially the exact same thing. They're equivalent to each other. One's the hydrogen ion, one is the hydronium ion. While a base is anything that has the ability really to produce hydroxide ions in solutions. And this is sort of your basic definition. And what we're talking about here is basically these ions floating around freely in solution, not attached to anything else, just by themselves. So if something has the ability to do that, it will make it a acid or a base, depending on which one that you see. A more sort of generic definition of an acid and base is a Bronsted-Lowry definition. And the Bronsted-Lowry definition, an acid is a proton donor. And again, this is also referred to as a proton. While a base is a proton acceptor. And the sort of consequence of the Bronsted-Lowry definition is it creates sort of pairs when we look at an acid-base sort of reaction. So if we have an acid plus a base, what's going to happen is the acid will donate the H plus over to the base. The result of that is it will create two things on the other side, which is known as the conjugate acid and the conjugate base. And there is sort of relationship on the left-hand side to the right-hand side. The acid on the left-hand side, its sort of partner and the guy that it is related to is the conjugate base on the other side, while the base and the conjugate acid are related to each other. Now, the relationship that we see between these two guys is really the relationship that happens when an acid and base gets together, and that is, it is this guy right here. So the only difference between those two things is that one H plus that has been transferred from the acid to the base. So when the acid goes to the conjugate base, it has one less H plus when it does that. And when the base goes to the conjugate acid, because it accepts it, it gets one more H plus as it goes from one side to the next. And that has to be the only difference that can be there, is basically one H plus. So if you have two things that are, you're wondering, are they related to each other through the Bronsted-Lowry definition? The answer is they has to be just one H plus. If it's anything other than that, then they are not related to each other. Even if they sort of look very similar or look like they're related to each other, if it is more than one H plus, if it is two H pluses or three H pluses, they are not related to each other in that sense. It is also important to remember that the H plus, that plus part of it is really important as well. And that plus part also changes the sign. So not only are you either gaining an H or losing an H, but you're also either gaining a plus or losing a plus. So things that lose the plus become one more negative, and obviously things that gain the plus there when the H plus gets transferred become one more positive. So on the conjugate side here, on the right-hand side, you want to make sure that you do adjust the charges for that plus, and that's a very common mistake people make, is they just kind of take the H out and not worry about the plus part of it. So it really does change what is there. Now, regular old acid and bases are usually always found on the left-hand side of the arrow there, and your conjugate acids and your conjugate bases are always found on the right-hand side of the arrow. Any questions on any of that stuff we talked about, I think, last time? Okay, so I think we did an example last time. So why don't you take a couple minutes here and see what you come up with. For each of the following, we want to write the conjugate base for each of these guys. So see what you come up with. Okay, let's take a look here, see how we're doing. So in this case, we're looking for the conjugate base. So remember that if we are not sure really what's going to happen, you should know that we are talking about really an H plus. And the key is, should you put it on or should you take it off is really the question. So in this particular case, we are looking to write the conjugate base, which means if we think about our reaction a second ago, the conjugate base on one side is related to the acid, while if we were looking for the conjugate acid, it would be related to the base. So in this case, we're looking to end up at the conjugate acid, which means a conjugate base, which means each of these things here are acids. And that should then tell us, based on Bronsted-Lowry, the definition we should do, which is actually donate an H plus. So each of these guys will act as an acid. It will donate its H plus. When it does so, it will be left with the conjugate base. So basically, we're just going to take an H off of this guy, which leaves us an H and an S. And again, in this case, it was neutral. So we also lost the plus. So we become one more negative in this case. So we end up with HS minus. Starting with HS minus, same thing. It's going to donate that H plus, which means when we lose the H, we are left with an S. It is already -1, which means we become one more negative, and it becomes S2 minus in this particular case. Any question on those two there? NH3, same idea. We're going to take off an H, which is NH2. And once again, here it is neutral, so it becomes one more negative in this case. And lastly here, H2SO3, taking off one hydrogen, leaves us an H, an S, an O, and a 3. And once again, we have no charge, so becoming one more negative brings us to HSO3 minus. So if you're not sure, if you understand sort of the relationship that's up there on top, you can just work your way backwards and understand what you are looking at. If you could determine that's an acid or that's a base, you could go by the Bronsted-Lowry definition and figure out what you need there. Any questions on any of that? Yeah. You're taking off an H plus, which is a proton. So you're actually losing a proton, which is because, again, in order for this guy to become H plus, the hydrogen has basically one proton, one electron, and it has no neutrons. So in order to become positively charged, you had to lose an electron, which leaves it really just a proton that's left over, which is why it's referred to as a proton sometimes. So you're basically losing more positive, so you have more negative electrons, and that's why it becomes more negative. Yes, sir. Every time you lose an H plus, you do become one more negative. So if you are -1 to start with, you become -2. If you're 0 to start with, you become -1 and so forth. Yeah. I'm sorry, what? You would just become one more negative, which would be +2, right? If you had a +3 for some reason. Yeah. So one more negative would be +2. Other questions? All right, why don't you try one here? Why don't we do HCO3 minus? Why don't you write what the conjugate acid would be? And why don't you also write what the conjugate base would be, starting with this guy right here. All right, so let's take a look. Let's start with the conjugate acid here. So once again, if you're not sure, we're going to be shooting for the conjugate acid, which means if I follow this back, what this guy is going to behave like right now is a base, which means it should accept the H plus. So in this case, he's going to add an H plus going this way. And that would give me one more H. And a +1 and -1 will give me 0. So we'll end up at H2CO3. And our conjugate base, like we did in the previous problem here, if we follow the trail backwards, in this case, it will actually act as an acid, which means it's going to lose an H plus. And the result of that is we will end up with CO3. We're already -1, so we will become one more negative, which would be -2, which is carbonate in this particular case. Any questions on any of that there? This guy, as you can see here, is able to act as an acid or a base, and there are lots of things or a number of things that can do that. A lot of times there are things that have a hydrogen and like a negative charge. Those guys are very popular to be able to kind of go both ways. Those things are what are known as being amphoteric. So an amphoteric substance is a substance that can act as an acid or base. I think we might have saw water the other day. It also can act as an acid or base. So things that can kind of go both ways are what are referred to as being an amphoteric. Any questions on Bronsted-Lowry, conjugate acid-base pairs, or anything like that? Okay. So let's talk a little bit about acid strength. The forward reaction and acid-base reaction, and remember when we see HA is sort of a just a generic acid formula. And at some point, some acids, which are weak acids, these guys can recombine and kind of go in the opposite way. And we get this reversible reaction here, which we do see with these arrows here. And this is what happens again in a weak acid situation. A weak acid is really a weak electrolyte. So a very popular weak acid is HF, which is hydrofluoric acid. Once again, when it does go into solution, it will actually mainly stay together. But it will produce a little bit of these guys. And once again, because it's still able to produce some H plus, it is considered obviously an acid. It is nowhere near a strong acid because of the reversible reaction. It will mainly stay together. Remember, whenever we see those arrows sort of heading in both directions, that's going to set up that equilibrium situation. And it is basically a weak electrolyte. And that obviously is very different than if we did come across a strong acid. And in a strong acid, it will 100% break apart and into its ions and be what is sometimes referred to as completely ionized. So unlike a weak acid, if this was the situation, maybe it was a small arrow, we would have basically 100% of what's on the product side in solution. You would have none of the acids still together in a strong acid situation. And again, that's why it's referred to as being completely ionized or completely dissociated. Once again, because of that, what you do is essentially create a lot of free H plus relatively quickly, which is why it's considered, again, a strong acid. If you obviously have the other situation happening where it's kind of going back and forth and really kind of hanging out over here, once again, like on the previous page there, that is going to be our weak acid. And just for comparison purposes, in a weak acid, you will have pretty much the acid still together, but will be able to produce a little bit of ions as well, a little bit of H plus. So in comparison to strong acid, pretty much just needs to go for a swim. It will produce a lot of H plus really quickly. And that is obviously why it is a strong acid. The weak acid's got to kind of work for it a little bit to produce the H plus, and you're not going to get anywhere near the volume of free H plus floating around that solution. Any questions on that there? There is a couple of important sort of relationships that helps us understand why certain things happen. But there is a relationship between an acid and even a base and sort of its partner on the other side. So when you have an acid, its partner on the other side of the arrow is the conjugate base. And there basically is an opposite relationship between those two. If the acid you are starting with is relatively strong, its conjugate base will be relatively weak. So there's sort of an opposite relationship that occurs. And vice versa, if you start with a weak acid, the conjugate base will be relatively strong. Now, what we mean about sort of weak and strong and the conjugate base is, and it's a little bit outside the scope of this class, but what can happen is if you have a conjugate base that came from a weak acid or even a weak base, it can continue to react with water, and it can continue to react with water and change basically the pH of that solution. Could make it more acidic, could make it more basic. So it has the ability to kind of continue to react with water. Now, if you have a base, kind of the same thing holds. The base's partner would be the conjugate acid. And if you have a strong base, its partner will be relatively weak. And if you have a weak base, its partner will be relatively strong. And once again, it will be able to sort of continue to react with water. In a reaction which is referred to as being a hydrolysis reaction, it's able to react with water and in some cases produce more H plus and in some cases produce more OH minus. Now, when we talk about some strong acids, here's a list of some strong acids, and it's good to kind of know some of these strong acids because pretty much if it's not one of these guys, you could probably safely assume that it's going to be a weak acid. So some strong acids, as you see there, is sulfuric acid, nitric acid, hydrochloric acid, perchloric acid, hydrobromic acid, hydroiodic acid. So these are 6 really kind of strong acids. And if you come across those guys, these guys will pretty much, with the exception of sulfuric acid in a sense, will 100% break apart into the ions. And remember, an acid, the cation is always the positive guy that is an H plus. There are certain acids that are diprotic acids, like sulfuric acid there. So if you take something like HCl, when it breaks apart in solution, it will break apart into H plus and Cl minus. It's able to basically release one hydrogen, and that is what refers to it as being monoprotic. It's able to actually dump off just one hydrogen, mono meaning one, obviously, protic meaning proton, able to give away one proton. Something like H2SO4, when it breaks apart, will break apart into 2 H pluses and a sulfate. And this is what is referred to as being diprotic, as it's able to basically give away 2 H pluses. There's also triprotic acids like phosphoric acid. Overall, what happens is it will dump off 3 H pluses and a phosphate here. Now, although a lot of times we will look at these reactions, sort of the overall reaction that happens, especially for something that's diprotic or triprotic, and it gives away 2 hydrogens or 3 hydrogens, we sort of think of the overall reaction. It is important to remember that it actually does occur basically 1 hydrogen at a time. So something like sulfuric acid will not just give away both hydrogens all at once. It's sort of a stepwise process at which that occurs. And so, for example, the first thing that happens is the sulfuric acid here will dump off just 1 hydrogen and make HSO4 minus. Then the HSO4 minus will then dump off the second hydrogen and make sulfate. So it's actually a two-step process that occurs when that guy loses it. We sometimes just kind of look at the overall reaction, which is what we have on the bottom. Is it easier to remove the first hydrogen or the second one? Which one's easier? It is actually easier to remove the first hydrogen. It is coming off of something that has no charge. Once you do, then the guy has a negative charge. You're trying to remove something that's positive. It makes it much, much harder to remove that. In fact, if you do the calculation, pretty much almost all of the H plus that comes off is actually that first H that comes off. It gets super, super hard to remove that second one. Same thing with something like phosphoric acid there. It is very much harder to remove the second one, and then the third one, barely any of it comes off in that process. Looks like we got off the screen there, huh? H3PO4 there. HCl. There we go. All right. Any questions on that there? All right. Now, a lot of acids are oxyacids. Oxyacids are pretty much what the name implies. They have oxygen in it, like acetic acid, for example, is a oxyacid, or even nitric acid, HNO3, has the oxygen in it. Something that has a carboxyl group, that is something like acetic acid, which is this. This is the carboxyl group. That is basically the main component of vinegar, sometimes written like this as well, or in formula form like this. And obviously, these are the guys that we talked about when we talked about naming. That is based off of the polyatomic ion. If it ends in 8, it ends in ic. And if it ends in ite, it ends in OUS. The ones that do not have oxygen are the ones that have hydro, like hydrochloric acid, hydrobromic acid, those guys. So water, as I mentioned before, and as we sort of saw, is an amphoteric substance. In certain cases, water can act as an acid. In other cases, it can act as a base. And water can even act as an acid or base with itself. So in this particular case here, water is acting as the acid that we saw earlier. Is going to donate the H plus. The result of that is we're going to form OH minus. By the way, I know that this will be a basic solution because I see OH minus on that side. In this case, it's going to act as a base. It's going to accept the H plus from the HCl, going to form H3O plus, which tells me this is going to be an acidic solution. And it is, because that's hydrochloric acid, which I would hope would be acidic. And the top guy is ammonia, which is a weak base. So obviously we would hope it would be basic. In this case, one water could act as an acid, the other water could act as the base. So in this case, when the H plus goes over, that water that lost the H plus will make OH minus. The H2O will make H3O plus on that side. This is what is sometimes referred to as autoionization of water. This is sort of what is happening all the time, sort of in water, in a water solution. And there is an equilibrium that occurs, and is this reaction here, which is our H2O, our H plus, and our OH minus. And if you remember from that chapter there, we can write an equilibrium constant, which is products over reactants, concentration of H plus times concentration of OH minus. This is what is referred to as Kw, the water ionization constant for water there, or equilibrium constant for water. And it actually equals 1 times 10 to the minus 14. So that is sort of a formula that you can use. The Kw equals H plus times OH minus equals 1 times 10 to the minus 14. Like we talked about before, a couple of things. When you see the little bracket, that means concentration. And that means molarity most of the time, which is our moles per liter. Also, as you can see here, you can substitute, as we talked about, H plus and H3O plus in for each other. So again, a lot of books like to write it H3O plus times OH minus equals 1 times 10 to the minus 14. So you always sort of have that number available to you. It's not always sort of given to you in problems, but you always sort of have that relationship sort of available to you. What is the relationship between these two things? Well, really the H plus part is the acid part of the solution, and the OH minus is the base part. So that's the acid and base part of the solution. And the way they are related to each other is as one goes up, the other goes down. So as the H plus concentration increases, you see a drop in the OH minus concentration. That means you have more H plus floating around in the solution. More H plus means that you are going to be more acidic. While if the H plus concentration drops down, then the OH minus concentration then will come up. So opposite relationship. And again, in that case, you would actually have more OH minus floating around that solution, which will make it more basic. And so really one goes up, one comes down. If they actually equal each other, then they both will have the same concentration in that solution. If you know one of those concentrations, either the H plus or the OH minus, then you could figure out the other. So if you know the H plus concentration, you can figure out the OH minus concentration, and you can compare the two values, and whichever one is larger will tell you whether or not the solution is acidic, basic. And again, if they're equal to each other, then it would be neutral. So by comparing those concentrations, if you get a larger H plus concentration, which once again is your acid part, is larger than your base part, then it's going to be acidic. If you calculate the OH minus as the base part is larger than your acid part, it's going to be basic. And if they equal each other, you will have neutral, and it will be 1 times 10 to the minus 7 in that case. The nice thing about the calculation is it's pretty much the same calculation regardless of which one is given to you. So whichever one's given to you, you essentially take 1 times 10 to the minus 14 and you divide it by the concentration. Most important in this chapter, again, a refresh. Make sure that you use your exponent button in this chapter. Otherwise, you are going to be off on a lot of these calculations. So you want to make sure that you punch in something like 1 times 10 to the minus 14, that again, you do use that exponent button. So like a 1, an exponent button, the negative button, and 14. So make sure that is how you punch these things in. You'll know that you're probably screwing it up when you calculate it, and like the front part of the number looks good, but the exponent part is just off. That's usually a good sign that you're not punching it in correctly. Any questions on that there? All right, well, let's try our calculators. Yes, let's see how they do. All right, so for each of these individually, 4 of them, calculate either the H plus or the OH minus concentration and determine is it acidic, basic, or neutral. So grab a calculator, make sure you know how to punch it in correctly here for each of these individually. So you should have 4 answers and 4 acidic, basic, or neutral. Okay, let's take a look and see how we're doing. So the good news is it's pretty much the same calculation. You're going to take 1 times 10 to the minus 14, and you're going to divide it by whatever concentration was given to you. So in the case of the first one, we were given the H plus concentration, which means we're going to take 1 times 10 to the minus 14, and we're going to divide it by 3.4 times 10 to the minus 4 here. Again, we want to make sure we use our exponent button. So that's 1 exponent negative 14 divided by 3.4 exponent negative 4. And that gets us a 2.9 times 10 to the minus 11. This is a concentration, so you do need a molarity there with it to match the molarity that was there originally. Any questions on that there? So once again, on your calculator, you should hit 1. You should hit the exponent button. Should hit the negative button. You should hit a 14. You then should hit the divide button. Hit the 3.4. Once again, exponent button. negative, and 4 hit equals. And again, no extra buttons along the way there. Yeah. Any questions about that? Yeah. Okay. Other questions? All right. So is this one acidic, basic, or neutral in this case? This one is going to be acidic. So what we want to do is really compare the H plus concentration to the OH minus concentration. And really at this point, you could just look at the exponents part. So that is to the -4, that is to the -11. That is a much smaller number, the -11, which means the H plus concentration is larger and it should be acidic in this case. Remember that when you have a negative exponent, the smaller number is the larger number, because times 10 to the -11 means you're going 11 places that way and putting zeros, which makes it a very small number, versus 10 to the -4, which you're only going 4 places that way and putting zeros. So the negative part is really important there from that comparison. Question on that one there? Yeah. Yeah, so if you're what you could really compare, you don't have to really compare the front part of the number there, because most of the time you will have like an exponent part. So you can compare the exponent part. They are both negative exponents, like -4 there and -11. The smaller negative number will actually be the larger number. Yeah. Yeah. It's actually a larger value. So so if we take this here, this is 0.0. If we turn it into a decimal, that is the H plus concentration. Yeah. We turn this into a decimal. That is the OH minus concentration. That is a much smaller number. Yeah, the larger exponent. Yeah. So that's why the negative is important there in the exponent part of it, because you're basically going to the left and putting zeros. So when it's to the -11, you're putting like 10 zeros in front of it, basically making a much, much smaller number. So the smaller exponent number is actually the larger big number. Yeah. Other questions? Okay. Let's take a look at the next one, which is 2.6 to the -8. So once again, here we'll do our OH minus, which would be 1 times 10 to the -14 divided by 2.6 times 10 to the -8. And we end up with something like 3.8 times 10 to the -7, I believe, molar. Again, on your calculator, it may not give it to you in scientific notation, a bunch of zeros and a 384 at the end there. In this case, we're going to compare, and in this case, it is actually the OH minus concentration is larger, which means that this guy would be basic in this case. Again, times 10 to the -7 is a larger number than 10 to the -8 in this particular case. By the way, when you are asked that question, there is really only one answer. When you're asked the question, is it acidic, basic, or neutral? Cannot be all three at once. Yeah, so sometimes people go with it's acidic and basic, so it cannot be. It's got to be one or the other. Let's take a look at the other one, 6.2 to the -9. This is actually our OH minus, is 6.2 times 10 to the -9. Really doesn't matter. It's the exact same calculation. Uh, 1.6 times 10 to the -6 molar looks like a winner there. Any question on that calculation? Once again, may not give it to you in scientific notation on your calculator, 0.0000, all that. In this case, comparing our concentrations, we once again here see it looks like in this case the H plus is actually larger than the OH minus, which means this would be acidic. Any question on that calculation there? Lastly, here we have an OH minus of 8.1 to the minus 3. And once again, we will be solving for the H plus concentration. 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. Yes, sir. I can't hear you. What's that? Is the third one basic? This one here? Is that the one you're talking about? Yeah. No, because times 10 to the minus 6 is a larger number. Because there's only 6 places to the left with zeros. The other one is 9 places to the left with zeros. Yeah. Other questions? All right, 1 to the minus 14 divided by 8.1 to the minus 3, it looks like. And my calculator wakes up here. Try that one more time. 1.2 to the minus 12. Yeah. And in this case here, we are looking at those two, and it is the H plus that is actually less than the OH minus in this case. So this guy would be basic. Again, to the minus 3 is a bigger number than to the minus 12 in this case. Any questions on that there? So really important to keep in mind that negative exponent, and again, the smaller number being larger, it's a very common error that people make. All right, let's try our calculator a little bit more here. All right, let's just calculate this, forget about which is greater. Just calculate the OH minus, and is it acidic, basic, or neutral here? So in this case, our OH minus here, once again, 1 times 10 to the minus 14 divided by our 2.8 times 10 to the minus 5, going to get us not that, try that again. It's going to be a 3.6 times 10 to the minus 10, it looks like. And once again, it does need molarity there. And in this case, upon comparison, we see that the H plus concentration here is to the minus 5. Our OH minus to the minus 6, that means that our H plus should be a larger number than our OH minus, and it should be acidic. Any questions on KW? How to use it? The key is make sure you definitely use that exponent button now. Okay, I think we're going to skip that one. Let's get into then the pH scale. The pH scale runs from go this way, 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And technically speaking, dead on 7 there is neutral. And that is because that would be the point where the H plus concentration would equal the OH minus concentration. And they both would have a value of 1 times 10 to the minus 7 molar, which would give you actually a pH of 7 on those. 7 is sort of your center point. As you go from 7 towards 0, you're becoming more acidic. As you go from 7 to 14, you're becoming more basic in that case. To calculate the pH, you can forget about everything that's on the screen there, but basically the pH is equal to minus the log of the H plus concentration. Once again, this is another formula where you can insert the H3O plus, and it's the same thing. Now, this equation, this formula here, and all of the rest of the formulas we're going to see in this chapter, depending on the type of calculator you have as to how you should punch it in. So if you got a display calculator, you should punch it in exactly the way you see it. You should hit the negative button. You should hit the log button. Then you should put the H plus concentration in it. If you have a non-display calculator, you need to do this equation, all the other ones, the opposite way. You need to kind of go this way. You need to start with the number, then hit log, and then hit the negative button. So negative, log, and number, log, and negative. If you're not sure what type of calculator you got, hit log. If it says log, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So if you hit log, it'll either say log or say error, and I'll tell you which one you have in that case. We also, again, want to make sure that we do put our number in scientific notation using our exponent button there. All right. Let's talk about significant figures and pH. When we calculate something like pH, the number of decimal places that the pH value should have is equal to the number of significant figures in the concentration unit. So in this case, we're going from significant figures to decimal places, and you would go backwards as well from decimal places to significant figures if you're going the opposite way. So why don't you try this? First, calculate the pH here to the proper number of digits. That's not negative, it's just from PowerPoint. So what is the pH here? And is it acidic, basic, or neutral? So why don't you take a second, make sure you punch it in correctly, depending on your calculator, and see what you get for the pH. All right, so first off, you should get a pH of 5, I hope, first off on your calculator, yes. So once again, that is negative log and then 1 times 10 to the minus 5 here. Put it in our calculator there, 1.0. Now, the answer should be 5. Should it be 5.0? Should it be 5.00? Should it be 5.0000000? Feels like a lot of zeros just to begin with, so I'll eliminate that one. What should the correct pH value be reported as? What do we think? It should actually be this one right here. Our concentration here has 2 significant figures. Since it has 2 significant figures, that gives me not 2 significant figures, but gives me 2 decimal places. So we're going from significant figures to decimal places, and then we obviously would go the opposite way if we had the pH back to the concentration, decimal places to significant figures. Any questions on that one there? That is a 0. By the way, is acidic, basic, or neutral? It is acidic, right? Less than 7. Any questions on that there? All right, so let's try a couple here. For each of these solutions, calculate the pH, and again, determine is it acidic, basic, or neutral for each of these. Okay, let's take a look here. So as was the question at the beginning there, the pH is minus the log of the H plus concentration, which means you definitely need the H plus concentration. In the name, it tells you that pH means you need that H plus concentration. So for number 1, we can roll right in. Our pH would equal minus the log 2.1 times 10 to the minus 5. And that would get us, once again, make sure you use your exponent button, 4.68. Any questions on that one there? That would then be acidic. And once again, to punch this in, if you have a display calculator, you should hit your negative button. You should hit the log button. And you should go 2.1, exponent button, negative, and 5. Yes. You got -4. So try punching in exactly the way I just did there. If you have a non-display, you should start with the number. And then hit the log button and then hit the negative button. Yeah. We'll try it one more time, just to make sure. Minus the log of 2.1 exponent minus 5. It should be 4.68. In this case, 2 significant figures, 2 decimal places. Again, not sig figs, it's sig figs. Question on that one there? Yeah. Number 2, we actually have the OH minus given to us, not the H plus. So we do need the H plus. So we might want to use our KW here. 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. Gets us, we'll call it, I don't know, 1.7 times 10. Too many zeros. 1, 2, 3, 4, 5, 6, 7, I think. Minus 7 molar. Now that we do have that for our H plus, our pH would equal minus the log of 1.7 times 10 to the minus 7. And if we do that, it's going to take the whole number there. We end up with a pH of 6.77 in this case. And that would be slightly acidic. We're going to go with 7 on the nose as neutral, just to make sure it's very clear. So anything above 7 would be slightly basic. Anything below 7 would be slightly acidic. Now, if you got this particular number for the second one, like 7.23, what you calculated was not the pH because you used the OH minus concentration. You calculated what is known as the POH, which is minus the log of the OH minus concentration. And if you do that, you will get what I wrote there. And that's not necessarily a tremendously bad thing because although that is not the pH value, there is a nice relationship between pH plus POH, it equals 14, which means you can get the pH by taking 14 minus 7.23, which will give you 6.77. That is here. So you were just a couple of slides early there. That is pH here, since it's off the screen. So you do need the H plus or the H3O plus to calculate the pH directly, but this is a nice way, as you can see here, you can kind of shortcut without having to use KW, and you can get to the pH pretty quickly, but you could also still use KW as you saw there to do that. So if you got 7.23, that was not the pH, but that is what is known as the POH. Any questions on that? Yeah. It is. So it's a good, easy way of doing it. Yeah. You can still use KW if you like, and we're going to see officially the POH here in just a second. But that is a nice way to kind of quickly calculate a lot of things, depending on sort of what is given to you. The pH scale is based on the log scale of 10. So by every sort of times 10 to the minus 1 change that occurs in the H plus concentration, the pH changes. So by the way, if you have 1 times 10 to the minus 3, the pH is 3. 1 times 10 to the minus 4, the pH is 4. 1 times 10 to the minus whatever will equal the exponent if you calculate the pH. As the H plus concentration increases, the pH gets smaller, it gets more acidic, and that's because more H plus, less OH minus, and vice versa. Less H plus means more OH minus, and more OH minus would mean the pH would go up in that particular case. So since we talk about a couple ways to measure pH, on the left there's a pH meter, which basically does a chemical reaction. It measures basically using voltage the free H plus concentration that's floating around in that solution, and it gives you a number, which is a really good way to measure the pH. They also have pH paper, which is kind of what we got going on over here. pH paper, if you ever had a pool or anything like that, or pool testing strips, you know, it's kind of the same idea. You dip it in the solution, changes color, you try to match up the color to what the pH is on the scale, and you can do it that way. Now, there are a couple other types of paper that we use commonly with acid and bases, but they don't necessarily measure pH. But litmus paper will tell you if a solution is acidic or basic. Typically, if your litmus paper turns red or stays red, it's acidic. Again, doesn't give you the pH. Or if it turns or stays blue, it is basic. So that's the use of litmus paper. Sometimes you just want to know is it acidic or basic, not really what the pH is. We use litmus paper a lot. Obviously, you want something more specific about the pH. pH meter is a good way to go. And or you can use pH paper. Obviously, pH meter would be much more accurate, probably. Here is our pH scale. And again, we see some strong base up here on top, like sodium hydroxide, our strong acid towards the bottom. We have pure water there that is 7. If I take the pH and put a pH meter into water that's been sitting out, will it be 7, the pH? It most likely will not, and probably be like in this range over here, a little bit acidic there. Sometimes people are surprised, and that's because when you have some water and some CO2 in the air, they come together to make carbonic acid, which increases the H plus a little bit and brings the pH down and stuff like that, especially if the water's been out for a while. Yeah. It looks like it is, yeah, just slightly. You know. And again, there's a range where it's kind of, you know, neutral-ish. It's not so bad or anything like that, but it is slightly acidic. And here's some other things: vinegar, obviously lemon juice, ammonia, household cleaners, as we talked about, are basic. Now, we sort of jumped a little bit earlier there, but there are similar scales to pH, and this is the POH scale, which is this guy right here. And that is the POH tells you that you need the OH minus concentration to calculate that, minus the log of the OH minus, pretty much the exact same calculation. You punch it in the exact same way as you do your pH. And that is that nice relationship that, frankly, if you have the pH, you could get the OH by subtracting 14. Or if you have the POH, you could get the pH by getting the 14 minus it as well. Putting that together with our KW, these are some of our important little equations here. In addition to this, if you have the pH that is given to you, so if you are given the pH, off the screen, try that again, pH right there. From that, you can actually get the H plus concentration directly from the pH, and you do that by taking the inverse log of the minus pH. And on most people's calculators, when you hit the inverse log, that usually will put like a 10 and a caret, and you want to make sure it's negative pH at that point. To do the inverse log on most people's calculator, that is the top left button, like the second or shift. And that is the log button, which usually has like a 10 and an X above it. And that's what you need to hit to do that. You also, if you have the POH, you could get the OH minus concentration from it. By the way, that equals the H plus concentration. You can get the OH minus, which would be the exact same calculation, the inverse log of the minus POH. And once again, that's usually a 10 and a caret minus POH equals that OH minus concentration. So those also are a couple of helpful calculations that you can do to kind of get yourself what you're looking for there. Any question on that there? So there are a number of different ways you could solve a problem depending on the information given to you. There's no necessarily wrong way as long as you pick a legitimate way to do it, and some can get you to the answer maybe a little bit quicker than using some other things. Why don't we try one here? Calculate the pH, the POH for each of these. And while we're at it, is it acidic, basic, or neutral here? So see what you come up with. And while we're at it for this one, why don't we also calculate the OH minus concentration? And this one, let's do the H plus as well. Okay, so we're gonna end. Why don't we take a look at the first one here? So since I have the H plus concentration, I'm looking to solve for all these things. I could do two things right off the bat. I could use KW like we did before, get the OH minus. I could get the pH. So I'm going to do that first. So I'm going to get the pH of that first one by taking minus the log of 3.6 times 10 to the minus 9. And that would be, not that, minus log 3.6 to the minus 9. It's going to be a pH of 8.44. Honestly, since I also want the POH, I could simply just take 14 minus that, and that would give me my POH. So do a little minus 14, gives me a 556 in this case. Any questions on that there? Now, instead of using KW to get the OH minus, since I do have the POH, I'm going to do that the OH minus will equal the inverse log of the minus POH. Once again, when you do like your second button, your log button, it probably will put a 10 and a caret up there. Make sure you hit your negative and make it 5.56. And if I do that there, find that on my calculator, there it is. I will end up with 2.8 times 10 to the minus 6 molar. Once again, I'm going backwards here. So this has 2 decimal places, 2 sig figs coming this way. Now we have these 3 answers here. pH is 8.44, POH is 5.56, and our OH minus concentration is this acidic, basic, or neutral, this one. This one is basic because of the pH. Once again, it should only be one answer for that. And this is a very common place where people give 2 answers because they go, my pH is above 8, so it's basic. And then they go, cool, my POH is below 7, so it's acidic. And they give both of those answers. You should always look at the pH because that is the scale you probably have in your head. The POH scale runs opposite. So if you have a low pH, you have a high POH and vice versa. So they are opposites of each other. So most people have the pH scale in their head. So always look at the pH value, determine if it's acidic, basic, or neutral. Any questions on that one there? Okay, so we will we'll lay it up there for today.